Hello and welcome everyone. Have you ever tried to use your terminal once, like using a language like Python or C or JavaScript or whatever was the programming language, and have you ever tried to add up two values like 1 plus 2? The result supposedly and without any thinking is gonna be 3, and we have tried it on a Python terminal here and it became 3. You can also try it on the console on the Chrome or Firefox or whatever is suitable for you to program it on JavaScript, and you'll find it to be 3. But have you ever tried to do 0.1 plus 0.2? You'll find out that the result will not be a whole number of 0.3, but it will become 0.3000000, and there is an end number at the end. So how is that even possible, and is that even correct? Like, yeah, it's not that wrong, but like that's a different number than the expected 0.3. It's not the specific one. So here we are going to explain why is that a thing and why does programming languages fall into that, and today we are going to explain that. So in the world of integer math, everything makes sense. 1 plus 2 equals 3, and it's comforting and reliable. But at the moment you introduce a decimal point, you enter a different dimension, a dimension where basic arithmetic breakdown. So welcome to the most famous what is going on in programming. So moment you become a beginner programmer, you type 0.0, 0.1 plus 0.2, you get this strange result. So even on multi-$1,000 machines and hands, it still makes that failure. So if you post this screenshot on Reddit or Twitter, you will get thousands of upvotes and thousands of comments saying welcome to the floating point maths, and read something called the IEEE 754, and they will add up noob for it, because they are just sometimes they are just bad out there. Okay, so they tell you read this IEEE 754. This is the standard for the floating points that these computers use. So why did this happen? Is your computer actually bad at math? So no, your computer actually is incredibly precise. The problem isn't math, the problem is this translation error between human world and machine world. So today we are going to look at how under the hood there's exactly that exclusive 0.0000 comes into place. Okay, so so we have firstly we're going to talk that there's a language barrier, which is that the humans do math at base of 10, the base of 10. So base 10, or sometimes we call it like we call the numbers and undernoted here or subnoted by 10. So we have, why? Because we have 10 fingers in our hands. Yeah, so it's intuitive. Our entire numerical system is built on powers of 10, tenths, hundreds, thousands. Yeah, so the computers don't have fingers. They have switches, which goes from either 0 or 1. Yeah, so they are binary. Transistors goes on and off, 1 and 0, and do the math on base of 2. Okay, so the computer needs to do base of 2 because it just has 0 and 1. Yeah, so the decimal number 5 translates perfectly into the binary of, like, let's say number 5 translates to binary of 101. Yeah, so it's not that the data is lost, but it's represented in another form. Yeah, so this crisis begins when we deal with fractions. So before we blame the computer, let's look at the flow of our base 10 system. So let's do a fraction. Let's say we do for instance, let's do 1 over 3, the fraction of 1 over 3. So the fraction of 1 over 3 is resulting for 0.3333. Yeah, for endless 3's. So the 3's will go just to the end of the screen. Yeah, so the 0 point the three just is repeating forever. You cannot write the number down perfectly in a piece of paper even, yeah. So you eventually stop writing threes. You stop at the fourth three, fifth three. They call that, sometimes they call the precision. So eventually you have to stop writing threes, and this moment you stop, you introduce an error, yeah. Even if you stop at the 500th, the 500th, so this is not the perfect, like, well, should I stop at the 1000th, like, should I do a 3 1000 times? Whenever you still go on, it's just still introducing less error, but whenever you stop, you introduce that error, yeah. So it's not the perfect number when you stop. So how will the computer even do that? Like, the computer, when will it stop? And especially when it does complex mathematics like banking or monetary, or things that actually need precision in numbers. So that 0.3 is just close enough to 1/3, yeah. So some fractions that look clean in the base are messy in another. So in base 10 it's messy, yeah. It's like third, it becomes 0.3333, but in but let's say 1/10, this becomes clean, it's just 0.1, yeah. Simple as that. So in the 10th it's simple to do, but in binary your denominator options are only powers of 2. You either have a things like halves and quarters and eighths, like 0.125. Since like you have powers of 2, like it's 1/2, it's powers of 2, like they have two options, 0 or 1, so it's half, or 1/2 power 2, or 1/2 power 3, which are these numbers representing these numbers. So how can I do this 0.1 now? The computer cannot represent this, or can it? So the computer has to figure out the combination of these binary fractions that this adds up to be exactly 0.1. Okay, so if you have to take 0 halves, like take quarters, you can make 1/16, yeah. So here is the shocking truth: the number of 0.1 does not exist in binary, yeah. So you get nothing but a repeating function that tries to imitate or get this something as close as 0.1 through the binary. So if you want to try to do 0.1 on binary form, you will find that it's 0.00001100110011000, and just repeats to be 00110 endlessly. So that's repeating forever. How am I, as a computer, or even an old computer, 8-bit computer or something, I was able to store a number like this? It was almost as impossible. So 0.2 has exactly the same pattern as 0.1, just shifted over one spot, okay? And still even remains forever. So here where our third part comes in place, where it is the IEEE of IEEE 754, okay? So I keep on missing this one. Okay, so 754. So this IEEE standard solve this problem, yeah. It, as we said, like 0.1 and 0.2 are endless numbers, so are endless binary codes. So what if our computer memory is not infinite? Like there's a 64-bit double precision float. Think of it as a suitcase. It can hold only 64 items. So when you tell the computer store me 0.1, which is endless, you're telling me I cannot store it. I'll just need a full computer to store one value. So it packs. Now we want to pack this zeros, ones, and 0, 1, zeros, but eventually. So under the standard rules, computer use something this standard, which gets the 53 bits of actual digits, which is significant. Once it hits 54 bits, nope, it just snips out and tells you this is enough. So it has to chop a number off. It rounds it to fit the corner. So the number stored in the RAM isn't 0.1, it is the closest possible value to 0.1. So the closest possible used in 53 binary approximations of 0.1. So let's do a visual presentation or something. Like, let's say we want to do let's say we want to do like 21185. They want to do the 0.1. It's the 0.1 is gonna become 101 1.00000 and a huge number of zeros, 5551115, and amount of values, bits, until it reaches 54 or 53 bits, and here it stops. Okay, this stopping introduces an error, but it's a very minimal error. So computing this on trinomial calculator, or that's just a bunch of zeros and 5 1 to reach a number like 0.09999, which is almost as close as 0.1. So yeah, so on a digital workspace representation, we're gonna show that this is we have reached the problem, or the main cause of this problem. That what here actually happens, that step 1, the computer takes closest binary approximation. Okay, so closest binary approximation, so it approximates this binary value. Then on the second step, it takes the closest approximation to the value. So it goes slightly off by a small differential, like it can go bigger than like small differential, like if it was 0.1, it can be 0.0999, or it can become 0.1000001. Yeah, so these are very close to 0.1. So, and these on the third step, it adds those imperfect binary numbers together. So when you add those approximation, the tiny error at the end binary strings compound and they add up, resulting in a binary sum that's not perfect binary representation of 0.1, 2, or 3, but slightly larger like this. Yeah, so the computer has to show the answer in human language, as this is the fourth step. After this have addition had added, it's supposed to show or print this value. When it printed this value, it prints it as a base of 10, and when it prints it as a base of 10, it takes it as a larger than this value by very slight value, and converts it back to decimal. So that's why a number like 0.3 becomes for us, as in binary form, to be 0.3000000. It's not binary form, but like approximated after the becoming binary, to be 0.0004408 and a very big value. And then we want the closest thing for the computer, for the human to see, which here becomes our initial value that we have got from 0.1 plus 0.2, which is 0.3000004. So the computer didn't make here a mistake in addition. Actually, no, it was the most suitable storing for this addition, and it was as perfect as a big amount of zeros than a 4. So if you try to calculate this with an 0.5 or something, it wouldn't create a very big of a problem. It's so far away, it's so precise, up to, let's say, 54 bits away. So knowing this, why does this matter? So building a video game that the character position is off by, let's say, 0.0000004 pixels, nobody will actually care. The floating point is fast. It's good enough for graphics and physics simulation. But we have if we are working with a bank handling billions of transactions a day, so money will be of a loss for you sometimes, or even of a loss to the client. Yeah, so and never ever using never use floating numbers for money. These tiny errors add up, and suddenly you lose few cents and few dollars. People get fired for that. So there are two ways to fix that. So firstly, you must use floats. Never check if two numbers are exactly equal. Like in programming in Python or JavaScript, there is something called A is equal to B, but this is the comparison of equality. Yeah, so like don't say if A is equal to B. It will never show up to be exactly the same thing. So let's try if we say let's show that for us. If you tried on Python doing 0.1 plus 0.2, is it strictly equal to 0.3? It will output false, which is something weird. Like for a simple human looking at this saying 0.1 plus 0.2 doesn't equal to 0.3, he will say that no, that this is corrupt, this is broken, this is not correct. So in return, to solve such problem, because like if you are searching for some strict value like 0.3 and you thought this is the addition of 0.1 and 0.2, then you must solve this problem somehow. So the best solution for this in your codes is taking the snippet out. If absolute of the result minus the value we want, this value, let's say it's 0.3 for instance now from our value, is smaller than a delta. This delta is the change, the error itself. So let's say it's 0.00001, okay, then do whatever you wanted to do. Okay, so here it solves the problem of the error that was being caused by the excessive value. Yeah, so sometimes they call this value or this error, they call it epsilon. You find it in competitive programming. We basically are telling computer, look, this is the difference. It's smaller than a tiny thing we wanna ignore, so ignore that part. Yeah, so the second way to use data types is design by precision, is almost never use a language has decimal or big, so this was the first solution. The second one is never have decimal or big decimal, like double or so. Use something that has like consideration for this. For instance, in Python you can do from decimal import decimal. This is a library there called decimal. Yeah, and in this library you can print let's say print you're gonna write decimal again. You're just not gonna write 0.1 here, but you're gonna write decimal 0.1, and the same here for 0.2, decimal for 0.2, and it will now print 0.03, and this is the result we wanted as a human to read. Okay, so this library does the math, and the hard way, look at on a paper specifically, avoid these base conversation or this conversion errors. It's low, but it's accurate nevertheless. Okay, so the fact that doesn't at the end I would like to say that the fact that 0.1 plus 0.2 doesn't equal 0.3 is not a bug. It's not a bug. This is the conclusion here. It is actually a compromise. The trade-off to having a computer that has crunch massive calculation by lightning speeds using infinite memory, or using a finite memory, I mean, this is the optimal thing. So the next time you see that ugly little decimal, don't just get mad at your machine. It's doing the best it can to do conversion from the binary world. And thanks for watching. If you finally like this video, I hope that you subscribe and like, and thank you for watching, and please tell me more if I can fix something or I can improve, and I would love to hear your response. And thank you very much.